Okay, so I want to add something from last time. So we have the theorem for a power series with non-zero constant term. The multiplicative inverse also has radius of non-zero, radius convergence is also non-zero. And moreover, because we have this is true by our results on products, right? And also we can talk about quotients then. So if f has a non-zero constant and g is any power series, both have non-zero radius of convergence, then the power series g divided by f also has a non-zero radius convergence. So what do we mean by the radius g divided by f? It is a formal Fourier series obtained by g multiplied with the unique multiplicative inverse of f. Okay? Then, because f has non-zero radius convergence, one over s also has non-zero radius convergence. We prove this. And the product of two power series non-zero radius convergence also has a non-zero radius convergence. Okay? So, here we have the analytic functions, differentiations of power series. Okay? This is our lecture for today. And we first look at analytic functions. So far, we look at power series expansion at our origin. If let f be a function defined in some neighborhood of z0, we say that f is analytic at z0 if there exists a power series with radius of convergence r positive, such that for all z in the disk, okay, which is equivalent as saying z and z0 distance r less than r, we have fz is equal to this sum. Okay, so for each z in the disk, the sum converges, and f of z is equal to the sum. Okay, so what we mean is that given a disk, right, center z naught, right, if there's a power series with radius converges r, we consider the same circle, right, same circle, but we shift it to z naught, center z naught. Now we pick any point z in the disk center z naught. F of z is equal to, if we translate back, right, to z minus z naught, then f of the z is equal to the sum an of z minus z naught to the power of n. Okay, this is what we mean by power analytic function. Okay, so on an open set, we say is analytic on open set if analytic every point. Okay, and we know that, okay, if this power series exists, then must be unique, right? And this is just some terminologies, right? We also say that f has a power series expansion as z naught, right? This is very illustrative, right? Power series expansion, meaning that the value of fz for z near z naught are given by an absolutely convergent power series as above, right? Is equal to this. Okay. If S is an arbitrary set, then we say a function is analytic on S if it is equal to the restriction of an analytic function on an open set containing S. Okay. And now we have some theorems about sums, products, and compositions of analytic functions. So suppose f and g are analytic on U, so are f plus g, f times g, and f divided by g for z, g z not equal to u. They're analytic. And the composition of analytic function is also analytic. Okay. So here's the proof. Let's prove this. Fix and z naught and u. We write fz is equal to this, gz is equal to this for all z close enough to z naught, right? And both power series have positive radius of convergence, right? Then we know that 4.3.2, which is this one, right? If you read through this, especially this, okay, then we know that fz plus gz is going to be equal to this. If z times gz is going to be equal to this, which you know what is Cn, right? There's an R such that for all z and z naught, fz plus gz, which is f plus g z, right, is equal to this. Fz gz is equal to something like this, so they're all analytic, right? For the quotient, well, since we want to make sure that the denominator is non-zero, right? So gz can be written as this. It's a power series with non-zero constant term, which means that it has a multiplicative inverse. And it also has non-zero radius of convergence, right? And the reason why I recall this, right, if you read the statement and you actually recall this, right, then we see that the inverse with the inverse power series, the power series with input z is the output is equal to 1 over gz, right? So f over g, right? Because gz, what this means that 1 over g is analytic at z naught, right? Right, because this. Okay. Now we want to show the composition, which is harder, right? So to show this, well, pick z0 and u. Since G is analytic at this point, we have a power series, formal power series, with positive radius convergent, such that Gz is equal to this for z near z0, right? Within the radius of convergence, because of uniform convergence, G is continuous. Okay? So like for z and z not small enough, then this thing will be small enough, which means that this thing goes to 0, right? Okay, this is a typo. This is G of z naught, okay? G of z naught. Okay? Yes. So Gz is going to be equal to G of z naught plus some power series. And, okay, I just went to washroom, so I forgot what was happening, but okay, let's keep on. So we have Gz is equal to this, right, for z near z naught. Well, because of uniform convergent, right, within the radius convergent, we have uniform convergence, right, which means that G is continuous on some disk centered at z naught with radius delta. Okay, G is continuous on this. Gz is defined by this function. We're forget about, but anyways, right? Define something like this plus this, right? So, which means that in particular is continuous at z naught, right? So if z and z naught is small enough, right, z is not small enough, we have gz and gz not small enough because G is continuous, okay? So let me repeat this. So first of all, we know that in some neighborhood, gz is equal to this. But actually, by uniform convergent, G is continuous, which means that if we can make z and z naught further, even more smaller, we can make this smaller, right? So if we let w naught defined as gz naught, this is the reason why I put it here. I did it a bit, so okay, anyways. G z naught is in V, right? Because G is a function from U to V, right? So F is analytic at W naught, which is in V. Okay, so there exists a power series with positive radius convergence such that F of W is equal to A of W minus W naught for all W near W naught, right? Now, we're gonna let this big H of T be denote the composition of these two power series, which is another power series, right? This denote the composition of this and this, right? Which is this of, right? This is equal to, right? Is a composition of this compose this, okay? Now, we know that last time we proved this, right? We proved this, okay? So, like, we have an S, we pick an S, which is the same as we did here. We know that there's a positive S such that for all this, we have H of W, which is, okay, this should be W to the power of N. W to the power of N, right? Right, which is exactly what we did here. HW is equal to this WN. It is equal to this. Okay, so this is, right, this expression. So we can make S even smaller if we need it, such that Z and Z naught is, for all Z and Z naught close, S distance is S close enough. We have GZ is represented a power series, and also that GZ and GZ naught will be small. Okay? So we can further make S small enough such that every Z naught small enough, we have these two holes at the same time. Okay? Now, then we know that GZ minus W naught will be equal to this power series, so that from here, right, H, this is the power series, right, which is H of Z minus Z naught, which is equal to this with Z minus Z naught, right? But we have this GZ minus W naught, right, which is this thing, right, which is F of G of Z, which is F of G, the composition of Z. All right, so this is true for Z and Z naught as close to each other. Okay, so we get a power series representation of FG in the neighborhood of Z naught, right, which is this. Okay, so this we've showed our theorem that the composition of analytic function is also analytic. Okay, now let if Fz is defined as a power series, radius convergence R, then F is analytic on this open disk. Okay, so it means that power series are analytic. So to show that F has a power series expansion at an arbitrary point of Z naught on disk, okay, so maybe if we draw a picture, if you draw a picture, okay, maybe we don't need this, but anyways, if this is Z naught, right? If this is Z naught, okay, we can pick an S such that this is less than R, right? This is always doable, right? And we shall see that F can be represented by a convergent power series as Z naught, convergent absolutely on a disk of radius s, center z naught, right? So we get radius s, center z naught. Okay, maybe here. Okay, radius s. Okay, this is what we mean by this, right? So if we rewrite this and use the binomial expansion, right? Binomial expansion. If z naught is as close to, so if z is here, right? Or z is here, right? So if z and z naught are as close to each other, then, right, we have this is true, which means that this is less than r, right? Which means that this series converges absolutely, which is equal to this, right? It converges, right? Now we can rewrite the binomial sum. We can rewrite the thing inside this to infinity if we just define this thing is equal to 0 for k larger than n. Okay, then we can interchange the order of summation, right? Because we have absolute convergence of this double series. We may swap the summation, right? We swaps to these two to get that, right? Fz is equal to this, or we may swap the summation here, right? To get fz is equal to this, which is the k starts from here, starts to here, right? So, and yeah, and we have this, it's our bksk. And this also converges absolutely, right? Which is this thing, right? This thing. Well, this thing can be estimated by this, so I'll leave you to fill in the detail for the rest. Okay, so this also converges absolutely as was to be shown. Okay. So making a translation, the theorem shows that if f has a power series expansion on this signified as z naught, that is this. So this is a power series converges for all 0 less than r. F is analytic on this disk, right? So explicitly to actually see why this works, we're picking W naught in the disk and this, right? We would pick W naught, right? So W naught in the disk center at R. Sorry, I think should be S. No. So yeah, W naught is a vector from, sorry, not vector, the complex number inside 0R. So this plus Z naught will be this, right? And let S be such that this is true, and we write this, okay? So we can, the rest just follows, okay? Okay, so now we're gonna move on to the differentiation of power series, okay? So we define, okay, so read this. The formal derived series, which is we differentiate term-wise, we get a new power series, right? And we in fact gonna show that the derivative of this is equal to this. Okay, so it actually holds. Okay, so before that we need a two lemma, which is like first year calculus. First of all, is this limit is equal to 1. Okay, so we use induction to prove the Bernoulli's inequality, right? And then we can use the squeeze theorem, and we can show this is true for all n use contradiction, okay? Or positive integer, right? And the second theorem is that for two real sequences such that all positive, and this is true, so the limit sequence B and converges the limit B, which is positive and finite, then we have the lim sup of the product, which is A and Bn, which is equal to B times the lim sup of an. Okay. So I think, okay, so the proof I won't repeat it. So I've typed it out, and here is the solution. Okay. And yeah. Okay. So now we're going to prove our central theorem. It says that let this radius converges R, then the series, this, has the same radius of convergence. Moreover, the function f, which is this function, is holomorphic on a disk, and its derivative is equal to this. Okay, so we're going to prove it. So let's just prove part 1 first. And first of all, we have this is true, right? But the lim sup of NAN is equal to this, right? And this limit is equal to 1, right? And all these sequences, this one definitely, right? And that's positive for all n, right? In fact, this is non-negative, right? So, okay. Actually, if we have this, the theorem still holds, right? Because what we have did is that we have this and we multiply it, so this should still holds. Wait a second. Okay. Yeah, it doesn't matter. This will just be greater than or equal to, right? This will just be greater than or equal to, right? Yeah. Okay, doesn't matter, because if this is 0, then equal if they're positive. Yeah, okay. So, okay. Yeah, still holds. True. So maybe read through this again. Okay. Yes, so I've been checking. Yeah, true. Okay. Guys, this is pure mathematics, so we have to be 100% rigorous. Okay. So we have this for all n, so we can still apply it, right? So the lim sup of this times this is equal to limit of this, which is 1 times the lim sup of this, right? Lim sup of this. Right, so we have this. Okay, so is equal to 1 over r, right? Therefore, the series have the same radius of convergence, right? Then they converges absolutely for the same values of z. Okay, so the first part of this theorem is proved. And as for the second part, we want to show that power series is holomorphic derivative, right? So pick a complex number in the disk, let delta be such that this is true, encompass h such that this is true, right? Not 0 because we want h goes to 0, right? We don't want to divide by 0. So we have f of z plus h by definition. We expand this, and this is the remaining term of the power series expansion. Sorry, binomial expansion. I'm sorry. Okay, it's been a long day, so okay. And but anyways, we can estimate this, right? H less than delta, right? And this is equal to Pn of z delta, right? Now, since z plus h converges because z plus h, right, less than equal to z plus triangle inequality, right, and less than z plus delta, which is less than r. Right, so z plus h less than r, which means that f of this converges, right? And also, this series converges, this, which is this, also converges, so we can subtract these two from this. So we can cancel those, which gives this, right? So we find f of z plus h, this is fz, right? Minus this, h times h, what does matter, is equal to this, right? So the series on the right converges absolutely, right? And we divide by h to get this. So this is what we want. So now we're going to estimate this, right? Or we can just estimate this whole quantity. But notice that this thing, which is less than or equal to this, but remember, here is this one. So less than or equal to this thing. But the thing is that we must show that this is finite, right? We must show that this is finite, okay? Just for the sake of safety, right? We want to show that this is finite. Now, remember, we define this, right, from here, right? So similarly, we have Pn of this is equal to this minus the whole expansion, and ignore the first and second term, okay? So this is equal to an of this whole thing, right, which is this, right? Now, first of all, this converges, right, which is this thing here. And also, this also converges because this is true, right? This also converges. And this thing also converges by first part, right? This is really the formal derivative, right? Derived series, right? Right? So all these, and these converges, right? So by limit rules, this can be boiled down to this minus delta times this, right? So this is finite, this is finite, this is finite. So, right? So this whole thing is finite. This whole thing should be finite, okay? Okay, so we showed that this is finite. This is finite. And this is independent of h, right? For all h, we have this is less than infinity, right? Let me put it here, okay? So we have, remember back to this, right? We show this. Now, what we actually want to estimate is put in h here, right? So h of this is less than or equal to h of this thing, right? This is finite, fixed, right? And this is greater than or equal to 0 by default, I mean, right? So as h approaches 0, the right-hand side approaches 0 because this thing is a constant, right? Like m, right? Therefore, the thing in the middle approaches 0 as h approaches 0. But this thing is just this thing, right? So we show that this thing approaches 0, which shows that, right? Which shows that f is differentiable and derivative is given by this, okay? So remark that conversely, we shall see after Cauchy's theorem that a function is differentiable amidst a power series expansion. It's a very remarkable fact, characteristic of complex differentiability, right? So, moreover, from the theorem, right, if we just play around with this and you can differentiate like k times, right? F differentiate k times, right? You can use this for multiple times. You're gonna see that right, is equal to this, right? So HK is a power series without a constant term, right? So if we plug in 0 in it, this thing will goes to 0. So fk is 0, so ak is equal an is equal to this, right? And also notice the formally integrated series. Okay, the formally integrated series has radius convergence at least r, because its coefficient is smaller in absolute value than coefficient of f, right? So here's explicitly the explicit work for any this and for any positive integer n. This integrated power, this finite sum, write it out, factor out this, and each of them, this one is less than a1, right? This one is less than a2, right? And this is less than an, right? So this whole thing is less than or equal to this just original sum. But if we just take this to infinity and take this as less than r, so we see that this is bounded. This is a bounded sum, so it converges, right? Formally integrated converges absolutely. Well, since the derivative of this integrated series is exactly the series of f, right? Because if we drop the derivative, it goes to a n z n, right? The derivative of this, right? We have this, right? Which means that integrated series has the same radius converges as f, right? Right? Because we showed this is true. Right? Okay. So, well, if we deal with the expansion at the point z naught, right, then we still have our results, right? Let z naught be a complex number, radius converges r, let fz is equal to this. Then the series, right, this series has the same, well, this is just a copy. It was just copied directly. And for the second part, function f is holomorphic on the disk z naught r. And the derivative is equal to this, right? So for the second part, we just copy the proof from above and replace z by z naught, but fz is still f of z. So if we have this, okay, let's just go back to the proof. We go back to the proof. F of z naught is equal to f of z plus h will be f to an of z minus z naught plus h, right? So z will be equal to z minus z naught, right? Z will be z minus z naught, right? So p z minus z naught, z minus z naught, z minus z naught, z minus z naught, right? So converges, and because, okay, so z minus z naught less than r, right? And z minus z naught, right, is delta. So this z minus z naught converges, this z minus z naught also converges, right? So we see this converges, blah blah blah, and we can show this is finite because it just z by z minus z naught, z minus z naught, z now this converges, okay, right? You can see that they're all the same. You can see that they're all the same, right? And hence blah 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 blah, and yeah. So this is equal to z minus z naught and minus 1. See? So we're done. Right? And we also have, this is true, formally integrated series, right, with this, converges absolutely, such a derivative is equal to f. Okay. All right, so let f be a function open set u if g is a holomorphic function such that g prime is f. G is called a primitive. So what we have seen is that a function has a power series expansion on a disk has a primitive, which is the formally integrated series, right? If a function has a power series expansion, then this is the derivative, is the primitive of it. In other words, any analytic function has local primitive at every point on its domain. And the domain must be defined to be open, I guess. Okay, but anyways, right? So this is everything for this lecture, and I will see you guys next time.